in an uncertain existence, the fact that the universe is expanding is one of the things that we know for sure. When Edwin Hubble was a young man in the early 20th century, the best scientific minds of our time thought that the universe was either static or deaccelerating due to gravity after the Big Bang. But as Hubble looked out into the stars in the galaxy, he noticed one thing. When comparing the redshift of different stars and different galaxies, he kept noticing that they all appear to be moving away from us. Every single one, every star and every galaxy that he could observe was moving either away from the solar system or from the galaxy. And even more interestingly, the further away the observed star or galaxy was, the faster it appeared to move away from us. It was directly proportional. As time went on, better optics and better technology and techniques allow for better observation of stars and galaxies further away, and the results were confirmed. The further something away is from us in space, the faster it appears to be accelerating away from us. And this is something that was noticed in every direction of the universe. Why was everything in the universe trying to run away from everything else? Hubble was a young scientist when he made these observations. He had only come back from volunteering from the Great War a few years, and Hubble had just completed his PhD. Is it possible that he had made some mistake in his notes? Is it possible he had made a mistake in his observations? Could all of his measurements be wrong? Little did he know he had made one of cosmology's biggest discoveries in our lifetimes, the discovery of dark energy, or the energy to which we attribute the continuing acceleration of the universe. The universe is expanding in every direction that we can see, no matter what direction we look in, towards the galactic core, away from the galactic core, perpendicular in either direction of the plane of rotation of the galaxy. One thing was constantly true: the further away a star or a galaxy appeared, the faster it appeared to be moving away from us. And we could tell this through what we call redshift. Redshift is a methodology for determining how quickly something is moving away from you, or in the case of blue shift, moving towards you, based on the shift of its emission spectrum. If we know what the light of a star looks like in terms of its spectrum, if we measure it and we have a shift, we can use that shift to determine how quickly that star is moving away or towards us, how quickly that star is moving relative to us. We may have thought the universe was like an ocean, that one day we could send expeditions to other islands to explore. We thought that one day, through brilliance and technology, we'd be able to send our astronauts and cosmonauts to the farthest stars, that we would be able to explore the universe and the galaxies just the way that we explored the Earth, that we would discover new worlds among the stars, fly in between solar systems, and reach the distant corners of the universe, that we would build cities among the moons and unknown new planets. We might have thought that humanity would be a galactic or a universal civilization over time. But how do explorers set sails for islands that are moving away? To islands that are moving away from us faster than our ships can sail? How could our astronauts and cosmonauts reach other solar systems, stars and galaxies if they're moving faster away from us than our fastest spaceships can go? Is humanity condemned? Is humanity trapped in the solar system? Will we never be able to leave it? At least not with our current understanding of how space-time works? The universe is expanding. According to what we know, the universe should be contracting. But humanity is not blind. We are not completely lost. We still have all the knowledge that we've built up over millennia. Hundreds of men and women around the globe, across time, working tireless to understand and describe the physical universe and world around us. The nations of humanity has spent immense energy, time, and capital in trying to unravel the mysteries of the universe. But how could we be so wrong in our understanding of gravity? Whereas the laws of gravity as we understand them now would tell us that due to the gravitational interaction, the universe expansion should be slowing down, eventually stop, reverse direction, and then lead to the big crunch. We know about the conservation of mass. We know about the conservation of energy. In our galactic vicinity, we're able to predict the motion of celestial bodies with our understanding of gravity. So what was so wrong? Why, when you applied our knowledge of gravity on a large enough scale, it breaks down? What is in the universe that we cannot see? What is in the universe that is accelerating the expansion of space-time that we cannot detect, touch, hear, see, or even know that it's there? We only assume that it's there. And since we can't see it or interact with it, we say that it's dark. Since it relates to the motion of the stars moving further away from each other, we call it an energy. Hence, dark energy. But what does this say about our understanding of the universe when we cannot account for 68% of the energy balance of the universe as best as we can calculate it? If the universe started with a Big Bang and mass and energy is consistent, shouldn't the universe be deaccelerating? But that's not what we're seeing, completely contradicting what we expect to find when applying the laws of gravity to the universe. We weren't just a little off, we were completely wrong. Instead of contracting, the universe is expanding. The theory of gravity would describe a universe that is contracting or deaccelerating, but not accelerating faster and faster. How can we reach the stars if the stars are running away from us? And we don't even know how. How do we catch them? So dark energy, that's what we'll call it. So this dark energy would be this form of energy that's completely around us, but we can in no way see or detect, not through our senses or through experimentation or instrumentation. If there's not a big crunch after the Big Bang, what happens when time goes to infinity? What happens to the physical universe? Does it keep expanding until all the galaxies and the stars can't even see each other, that the universe is so vast? In the end, all we have is theories about what constitutes the majority of the universe's energy that we know nothing about.